SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 11. We were talking about process FMEA, and in context of that we were talking about a problem of a wax lining on the door interiors between the inner and the outer member, where there were potential causes of failures associated with rusting of the painting body or painted body, or even rusting of the components like window regulators, etc., which are put inner inside the inner member of the door. There were various reasons or the causes due to which the failure would come. These were kind of identified, and the severity of the problem as well as the occurrence of the different causes of failures were sort of identified again and ranked in accordance. So we want to now look at the detectability. So let's come back to this particular check sheet that we were talking about in this context, where if you may remember we mentioned about the potential causes or failure mechanisms, okay, the column 14 of this particular check sheet, and then again rated the occurrence of this particular different mechanisms which would cause the failure to happen. And then we talk about the detectability, that is how easy or difficult it is to detect and rank accordingly. So we look at the current process controls which are available. Okay. So one of these, for example, the manually inserted spray head not inserted far enough, as I detailed last time. It has a visual check each hour, one per shift for film thickness, depth, meter and coverage. Okay. So the operator here has been instructed to probably stop the line and check, or maybe even in another case there is a supervisor of that particular zone which has been asked to do this visual check each hour, where he out of whatever number of vehicles are produced in 1 hour, one of the vehicles he takes and randomly picks it up, and obviously he varies his time, etc., on the principle of statistical randomness, whatever he wants to introduce in the observation. And then he checks for the film thickness, the wax film thickness, and also the thickness here is the depth in meters, of course, and also the coverage area of the wax within the inner and outer door. Okay. So here he finds out that by doing this kind of a manual inspection, maybe about 50% of the times he is able to make it out whether the defect is sneaking out of the system. Okay. So obviously it is one per shift, and in a takt time of let's say 2.5 minutes or maybe even like let's say 2 minutes, you have about 30 vehicles rolling out in each hour, and he is only checking on one. Okay. So based on that, still he finds out that there is only a 50% probability of detection of this manual inserted spray head not inserted far enough, okay, by doing the visual check. The other potential cause was spray heads clogged, and so he finds out what is let's look at what are the current process controls for preventing that from happening. So you basically test the spray pattern at startup and after idle periods, and obviously there has to be a preventive maintenance program to clean the heads from time to time. So the company has put in place some kind of a spray board where it sprays the by putting the nozzle or inserting the nozzle on the center of that board, and sees if the spray pattern matches the intended pattern that is supposed to come in a fully operational nozzle with zero clogging. Okay. So that's also again once in a while that he does this check, and then obviously this is aligned more towards either the startup period where the first vehicle has to be sprayed, and also after let's say any idle time in between, let's say the production line stop for some time for lunch or some other purpose. So during that time again he does the test spray pattern checking again. Okay. And there he is able to only detect these with 30% luck. Okay. So he has rated this particular detectability to be 3 out of 10, okay, the process engineer. Now you talk about the next cause of failure, which is spray head deformed due to impact, and obviously the only way to do it is preventive maintenance program, maintain the head from time to time, and there is almost a 20% chance of detection of this kind of a failure mode, okay, or a mechanism of failure, which is going to cause the deteriorated life of the door because of the rusting problems, etc. So he identifies this to have a rank of 2, okay, so the detectability is 2 here. And then finally, the spray time insufficient, where the occurrence was about 80% of the times, the operator instructions are given at that particular point, and a lot sampling of 10 doors per shift is carried on. So basically, let's say in a production level of about 200 or 250 cars, you are checking about 10 cars, and you're checking for coverage of critical areas in a very accurate basis by pulling out the cars either into a bay or something, and that helps you to prevent this particular defect of wax coverage improper up to the extent of 70%. That means the detectability really increases because of such a operator instruction from time to time and lot sampling from time to time, okay. So therefore you have now rated all the detectabilities of the various process controls which are used for identifying, or which are used for identifying the various mechanisms of failures related to either manually inserted head not going far enough, or related to either spray heads getting clogged, etc., because of viscosity, temperature or pressure issues, or again related to the spray head deformed because of impact and false practices carried out by the operators on the line, or spray time insufficient, okay. And this whole list of 4 causes have been identified in terms of their occurrences and rated, and also the process controls associated with them have been identified for the detectability, that with that particular control on, is it possible to detect it with a higher percentage or a lower percentage. So obviously the RPN has to be calculated by a product of all the severity, occurrence and the detection, and in this particular case the severity for this defect of the overall set of defects which are there in the automotive paint shop is about 70%. So 7 has been rated as the severity here, as you can see. So severity doesn't change for any of these causes, because these causes are actually leading, okay, to the failure mode which is being considered, okay. And so therefore you treat that as 7 uniformly all through, and you make the product of the severity in column 12, the occurrence in column 15, and the detectability in the column 17, and multiply them to find a RPN, or a risk priority number, of 280 for the first mode of failure, which is the manually inserted spray head not inserted far enough, 105 for the next head of or next mode of failure, which is the spray heads clogged, because of which this deteriorated life of door comes because of incomplete coverage of the waxes within the door inner outer wax within the door inner and outer, and then finally the RPN of 28 for the spray head deformed case due to the impact, and the operator 392 for the spray time insufficient. So obviously you have to now identify which is the mode of failure which is causing the highest RPM. In this particular case, probably, as you can realize, the 392 case which is illustrated here, okay, and the 280 are the 2 most impactful modes because of which the potential failure would happen. So you'll have to do something to prevent them on a very urgent priority, and then obviously you can keep the remaining ones. In this particular case, in fact, you can do a comparison for 3, because you have quite a high RPN value in 3. You can see 280 is for the first cause, that is manually inserted spray head, 105 is for the second cause, that is spray heads clogged, and 28 for the third cause, which is minor, and the fourth cause, spray time insufficient, is 392. So we can identify the first cause, the second cause and the fourth cause, and maybe just leave this untouched because it has a low RPN, so we need not really address it. Obviously when you do it for the second iteration, after doing some kind of a corrections or identified measures to counteract the potential causes, you will have to again probably pick it up, but at this time we are leaving it. So the 28 RPN is left over, which is corresponding to the spray head deformed due to impact. It doesn't happen very severely, or it doesn't happen many times, so you can leave it in fact. and then we only talk about 3 different aspects or modes causing this failure of incomplete coverage. One aspect is related to the manually inserted spray head not inserted far enough, for which the process control has been a visual check, okay, and probably each hour once in a shift, for the film thickness, depth, etc. Then you have the second cause as the spray head clogged because of viscosity, temperature or pressure issues, and there also you have to have a process control of a testing of spray pattern and some preventive breakdown maintenance programs which are there. And the third cause is the spray time insufficient, which is in fact very high, 392 and RPN. And here you are having a process control of operator instructions regularly or lot sampling of 10 doors a shift to check whether the sufficient time is being spent by the operator on particularly per vehicle, etc. And here you are getting the highest RPN. So you have identified these 3 different causes and you try to take a countermeasure at this particular step. So let's look at what are the countermeasures to eliminate these causes. So here, for example, the process engineer points out that if we add a positive depth stop to the sprayer, then there may be a chance of the foolproofing of this manually inserted spray head not inserted far enough. Okay. For example, let us say if the nozzle in this particular case, as you are seeing, has a tip, right. So this is the wax dispensing tip of the nozzle, and this tip is supposed to go into this particular region here, and it is going all the way into this region in this direction. Finally, even the nozzle comes to this particular point, it should start the dispensing. So if we can make a limit switch there, which can be pressed to ensure that the wax is coming out. So basically the nozzle has gone into this inner door and it is going to hit some particular region where there is a limit switch which gets actuated, because obviously the construction of the door is such that if you look at this is the inner member and this is the outer member, they together hem, right. So there is some kind of a bending of the profiles so that there is a hemming at the bottom here, and so there is less gap here, okay, in this lower end. So if the nozzle is going all the way down into that less gap zone, then maybe some limit switch or a positive depth stop can be actuated, which starts the flow of the wax, okay. Otherwise the wax will not come out of the nozzle. Then it may be a foolproofing, or as in the Japanese call this pokayoke, which can be placed so that whenever the nozzle is going into this smaller gap in the hemming region of the inner and outer door, the actuation of the limit switch because of a striking of the nozzle with respect to the inner or outer members is going to start the wax disposal here, okay. And before it has gone into that depth stop region, there is no emanation of the wax which comes out. So this would be a foolproofing that can be done, which they have recommended, and they have given a completion date and a target and a responsibility. So here the assembly engineering, the manufacturing engineering comes into picture, and some fictitious date has been given here for the manufacturing engineering. So obviously there are 2 functions attained here. One is obviously the depth stop, which gives or which ensures that the dispensing would happen or the limit switch would be pressed, and the other one obviously is that it is starting to automatically spray once that particular depth has been reached. So we can say that this is a depth stop providing automatic spraying of the wax, okay. So the idea is now that this door profile, as I showed you here, is quite complex. You can see the door profile to be in this particular manner here, okay. And so wherever there is this hemming region where there is a change of the gap between the inner and the outer member, because of which there is a spray actuation, the moment the nozzle reaches that particular zone, it ensures that the wax has disposed of. Otherwise the wax will not dispose of. So unless and until the operator goes to that particular region, the disposal of the wax will not be there, and it can be detected using the process control of a visual check of 1 per shift that has been done, and it is some kind of an automation, okay, based on which this would solve the problem of manually inserted spray head not inserted far enough. So the manufacturing engineer added this stop, and the sprayer was checked online, and the only problem was that once the automatic spraying method, which I illustrated earlier, was implemented by the manufacturing engineering, they find that it is rejected due to the complexity of the different doors on the same line. So obviously the gaps etc. between the inner and outer member of a multi-model production system may be different, because there are many other different assemblies, door assemblies which are being marked. So therefore the second solution of an automatic spray as the depth has come was eliminated, and only the fact that adding a positive depth stop to the sprayer, that is it's like a foolproofing that it would start the spraying, that was sort of added to the system, okay, and it worked out very well. So now they have done a severity detection and occurrence ratio here, and you see the severity is same because the defect does not get changed, or the overall severity does not get changed, but because of this countermeasure which has been taken of the depth stop, the occurrence has reduced from 80% to about 20%, and obviously the detectability is still the same because we have not controlled the current process control, which is a visual check, and that happens to be 5 in this particular case. So the overall RPN value comes out to be 70. So obviously the 280 RPN has been reduced to 70 because of the less occurrence of this defect owing to this automation that has been provided. Okay. So in this particular way you have reduced the RPN value by taking a certain countermeasure or a counteraction. So we are going to look into all the other failure modes which are there and different countermeasures in the subsequent module. In the interest of time, we will probably close this module right here and go ahead with the other modes of failures and the same analysis and how the RPN can be changed in a later on module. Thank you so much.